Okay, welcome to the last section of Chapter 3 here. We're going to talk about measures of relative position. So this is more about where a particular data point is inside a distribution. So there's a few different ways to describe that. We can use, sorry, I thought I had that selected. There we go. We can use, percentiles, quartiles, and what's called a five-number summary. Um, and we can use these to construct a box plot. So we may have heard the term percentile or quartile when we're talking more about standardized tests, for example. You might hear about somebody being in the 90th percentile on the ACT or things like that. So that's basically you divide the data up into equal parts and say which part the value lies in. So if I was in the 80th percentile, um, it'd be, you know, in that top 80% range of something. Um, so percentiles, we're dividing things up by 100. So we've got, for example, here we've got I is the location of the whatever percentile we're after. So that would be the data value corresponding to that percentile. P is the percentile we're looking at. So if I'm looking at the 80th percentile on the ACTs, that'd be 80. It is the number of data points. It's important to note that this is an get my laser pointer here. Needs to be an ordered array of data values. We're typically going by whole numbers. If we get a decimal value, we want the next larger whole number. So this I here it's the count of them. So so this is telling me that this formula is telling me not the data value. It's telling me which place I'm in. So if I've got 100 data points, or if I've got 75 data points, this formula would tell me that I'm looking at, let's see, 80th percentile, 75 times 0.8. You just do this real quick because I cannot do 75 times 0.8 in my head. So 75 times 0.8, so 80 over 100 is 0.8. If I've got 75 points, point number 60 is going to be the 80th percentile. And then I could look at my ordered array and see what point number 60 is, and that would be the value associated with that. If that, so I cannot have less than whole numbers of where something is in the list. I can't look at item 2.5 on my list of 5 items, right? So if I get a, if I'm on my list of 5 items, I get a 2.5, then I would use item number 3, next larger whole number. If I end up looking at okay, so formula results in a whole number. Huh. I missed this one when I looked through the test. So text. Apparently you average so if I was looking at item 2 on the list, I would average the values for item 2 and item 3 and report that as the percentile value. So here's an example. Let's go ahead, take a minute, work through it, and unpause when you're ready to move on. Okay, so they've given us the stem and leaf plot of the data values. Go back so you can remember what you're after. You're after the value of the 10th percentile and the value of the 20th percentile. And here is your data, or some of your data. And give you a minute. And here is the last bit of data. This is not overly useful in terms of being able to do the exercise. Let's see. Let me double check here. Okay, if you have the textbook, this is example 318 on page 159. So that would let you look at the data. Okay. All right, so this is an ordered stem and leaf plot. We need to remember that the location we get from that formula for percentile gives the location in an ordered array. There's 135 values. We want the 10th percentile, so P is 10. Plug that in. We get 13.5, round up to 14. Right. Approximately value 14. We find that 14th value is 17.3. Approximately 10% of the values are less than or equal to 17.3 would be what that percentile means. All right, let's look at the 20th percentile. Again, we just changed that one number. That changes from 10 to a 20. We're now looking at value 27, so we will be doing that, averaging the values that they've mentioned. Arithmetic mean of the 27th and 28th values, 27 being what we got from the formula, 19.2 and 19.3. So value of the 20th percentile is 19.25. So approximately 20% of the values are less than or equal to 19.25. So if you're in the 80th percentile on your ACT, then approximately 80% of the people scored equal or lower than you. If we have we can just rearrange that formula if we know the order of something in an ordered array. We can divide that by the total number, multiply it by 100, and that gives us the percentile for that value. But we just have to know where it sits in that ordered array. Okay, so if we're using the last state data set, we've got a car that averaged 20.1 miles per gallon. There's a couple of 21.1s. I could look at this and count where it is. If you've wrote the data down or have access to it, go ahead and do that and move on when you're ready. We have the data in order. All right, this is both in the 48th and 49th position, so we'll pick the one with the largest location. In was 135, location is 49. Plug those in, and we get about 36.3%. Or 36, I guess we'll round to whole numbers. Okay. I don't see percentiles used often outside of standardized tests offhand. I'm sure there are other applications. That's just the one I'm most familiar with. Quartiles are a lot like percentiles, except they're you're dividing things into 4 instead of 100. So we've got the first quarter, second quarter, third quarter. Pretty simple. This is somewhat more common because we use these for box and whisker plots or box plots, which we'll talk about in a couple minutes. Which can be a fairly nice way to view data, honestly. Okay, so let's look at the miles per gallon data again from the last one. You could find the quartiles. Approximation method. So we could use the percentile method to find the quartiles. Okay, sorry, I had to stop and read through the approximation method. So if we use the percentile method, we just use values of 25, 50, and 75 and find the numbers that go with that. That would give us the quartiles, the count values that go with the quartiles. The approximation method, we start with finding the median. That's going to give us the midpoint, the 50% mark, the second quartile. And then we take that upper range and find the median of that, and that gives us the 75%, or the third quartile. And take the lower range and find the median of that, and that gives us the 25%, or the first quartile. All right, so let's look at the solution. Again, the value is already in order, and we know that n is 135. So there's the values again. So the percentile method, we've got p equals 25. We still have 135 data points. So that's 33.7. We'll round up to 34, which is 19.8 miles per gallon, and that would be the first quartile. Repeat this with 50%. We get 67.5, round up to 68. So that's 23.6 miles per gallon. That should also be the median. The third quartile is the 75th percentile. Again, so we repeat the calculation and get 101.25, round up to 102, which gives us 25.3. Okay, so the approximation method, we divide the value in half. Odd number data values. So the median is exactly in the middle. Median is the 68th position, which was 23.6, which puts us at the second quartile for 23.6. Now we look at the median of the lower half of the data. That will give us the 67th position. We don't include the median in the lower half. The middle values be the 34th. So the first quartile would be 19.8. Do the same thing for the upper part. On the again, we not including the median in that, so we get 25.3. Gives us the same values either way. Okay. So let's find the quartiles of this data set, or these data sets, using the approximation method. So just check, yeah, those do appear to be in order. So go ahead and work on that and proceed when you're ready. Okay, so the first step is, of course, finding the median. Since in set A we've got 14 data points, so the median is the arithmetic mean of the 7th and 8th positions, right, which is calculated like so. So we get 70.5. So now we take the median of the lower half of the data, which is 65, and the median of the upper half, which is 78. So our quartiles are 65, 70.5, and 78. Okay, so let's again with B start with median. We have an odd number of values this time. Value is located in the middle, which would be 75. With the odd number, the median does not get included in the upper and lower halves as we're doing this. So find the median of those groups, excluding the midpoint 4. We get 67, 75, and 79. Quartiles get used in what's called a 5-number summary of data. So you give the minimum value, the first quartile, the median or second quartile, same difference, basically the third quartiles, and the maximum. You list them from smallest to largest. Minimum, first quartile, median, third quartile, maximum. So we could take the data from that previous example and write the 5-number summary. Or sorry, this is the example for the highway miles per gallon data. We've got a minimum of 12.1, maximum of 35.9, and the quartile ranges as calculated. These can give us a very nice, convenient way to plot this data. We can do this as a box plot, sometimes also called a box and whisker plot. So we've got the minimum value, the first quartile, the median, third quartile, and the maximum value. And this distance between the first quartile and the third quartile is called the interquartile range. It gets a little bit larger there. So this gives us both one of the measures of let me turn my highlighter back on. There we go. We get one of the measures of the center there. There's an idea of the range from that, and you get kind of an idea of the, well, not an idea of the range, the actual range. You get an idea of the spread based on where the quartiles are as well. So it's kind of a useful plot to summarize a histogram in some ways. As I said, the box part here is the interquartile range. That's the first to third quartiles. It's the middle 50% of the data. The whiskers are the lines that reach out to the maximum and minimum. So our formula for interquartile range. If we want to make one of these, we start with a horizontal or vertical line, doesn't really matter which. And we put the 5-number summary on it. Create a box in that interquartile range. And lines out for the maximum and minimum values to form the whiskers. So here's our 5-number summary from the miles per gallon data. Take a minute and make your box and whisker plot for this, and move on when you're ready. Let's see what you've got. Alright, so if we make a horizontal axis, label it at even intervals so that it's useful and not misleading. Just mark down our segments that we need. Create the box for our interquartile range. And make those whiskers. And there we go. Okay, so we've got some box plots from the USGS website. And they've got their explanation. You'll note here that these are, rather than the maximum and minimum, they're giving us the 10th and 90th percentiles. So keep this in mind, and let's answer some questions about this. Okay. And I gave away part A already. Those are the 90th and 10th percentiles. Highest median average spring total phosphorus concentration. So y-axis is total phosphorus concentration. Want you to note that in addition to showing the median here, the 50th percentile, also has a single dot on these ones showing the mean. Subbasin with the lowest average being mean, spring total phosphorus concentration. We go back here so you can look at that. Okay. And which subbasin has the largest interquartile range? Again, I'll go back so you can look at that. All right, let's look at the answers. Again, I gave that one away. Highest median average spring total phosphorus concentration was the Missouri. Lowest average spring total concentration. I missed those were the y-axis was an average already. So you do need to be careful and not read too fast. These are average spring total phosphorus concentrations that we're looking at. So rather than looking at the average total phosphorus concentration, we're looking just for the lowest. So that there it is at the Ohio, Tennessee. I was looking at that mean value and thinking those two were the same, but. And the largest interquartile range is the Missouri. That's, go back here, that's very easy to spot that. Okay, so the last new concept here is standard scores. You can compare two data values from different populations by essentially comparing their relative percentiles. You can also present data as how the values relate to the mean of the data set. This is called a standard score or sometimes a z-score. It tells us how far something is from the mean in standard deviations. So if I wanted to compare an SAT score and an ACT score, they're different scales, right? I could calculate where the two scores are in percentile and compare them that way. Or I could take them and look at the score minus the population mean divided by the population standard deviation and get this z-score, and that will tell me how many standard deviations away from the mean that value is. I can do the same thing for a sample. I'm using the sample mean and the sample standard deviation instead. Same thing, it's just the number of standard deviations away from the mean a value is. So for the SAT, if the mean is 500 and with a standard deviation of 150. We can calculate the standard score for a 630 easily. Got 500 and 150. Plug that into our formula there, and we get 0.87. All right, compare scores. So we've got two people. They're in different calculus classes. They both took a test. Jody is very happy with how she scored. She did better than the mean, and she was bragging. Her friend was a little upset because she only got an 82. The mean of her test was lower. Standard deviation was larger. So compared to the mean, which student did better? So we can calculate the standard score for this. Go ahead and do so and unpause when you're ready to move on. Okay, so let's start with Jody's score. Okay, we've got that. 87 minus 80 divided by 5, which gives us a 1.4. Ashley's score, same formula. So 82 minus 73 over 6 gives us a 1.5. So Ashley did better on her calculus test compared to her class than Jody, even though Jody had the highest absolute score. Ashley's score was more standard deviations above the class mean.